All right, hello team. Today we're going to be doing a review of series and convergence tests. We're going to be looking at geometric series, harmonic, and p-series, and the alternating series test. It is a relatively quick overview. If you want a little more of the practice and introduction, please make sure you go back to the Unit 10 lessons on my YouTube channel. You can go find those or in the BC Calculus page. If you need help getting there, let me know. But today we're going to kind of be tying some things together and doing a little bit of practice. It's going to move kind of fast though. Please do come to office hours if you need to. For those of you who are A/B test takers, you do not need to watch through the video. Your practice is in the PDF at the very end. It is 4 free response questions to practice and grade. Okay, that's how you should spend your time, and the videos and scoring guides will be online. All right, here we go. So today let's start with talking about a geometric series. Remember, a geometric series is a series in which we go from one term to the next by multiplying by some common number. All right, if this is a series we're looking at here, we could say that this is a geometric series because we're starting at some value. We call this a sub 1. A sub 1, our starting value is 1, and to get to the next level, each time we're multiplying by 1/3. This 1/3 is what we call our R value. And so for a geometric series to converge, a geometric series of the form a r to the n, if that R value, the absolute value of it, is less than 1, then the series will converge. Because essentially what we're saying is that it's getting small fast enough. We're multiplied by something less than 1, so this series will get smaller and smaller and smaller, the terms will get smaller and smaller. If the absolute value of that R value is greater than or equal to 1, then the series will diverge. That kind of makes sense because if we were each time we stepped up a level term, we doubled, then this, as we sum this up onto infinity, would just get bigger and bigger and bigger partial sums, right? So for each of these, let's go ahead and determine if the series following geometric series, we want to find the R value and determine if the series converges or diverges, right? So in this one, we don't have to do necessarily a ton of work here. We can see that the thing that is underneath the n is 2/3, so we can go ahead and say that R is equal to 2/3, and then therefore, which is less than 1, therefore the series converges, all right? So ultimately, actually, as long as you can see what that common factor is, what that R value is, it doesn't necessarily need to be in the form R to the n. If we wanted to, we could have rearranged this so that it was in the R to the n form. This would be 2/3 to the n minus 1. So if we wanted to, using our properties of exponents, we could have rewritten that inside part as 2/3 to the n times 2/3 to the -1. To the -1 means flipping that fraction, right? I could flip it to be 3/2 and multiply it by 4. That would give me 12/2 times 2/3 to the n. And notice our R value has still stayed the same. The only thing that changed is really our starting value is really 6. And we could have seen that if we wanted to by plugging in n equals 0 in here. We would have seen that the starting value is actually 6. But our R value doesn't change. Okay. Let's take a look at this one. What do we got here? This is a little harder to do though because this parentheses thing over here was grouped nicely to the n minus 1. But here we have 2 to the n and e to the n plus 1. So let's use some exponent properties like I did over here to kind of see what's going on here. This series, if I look at the n side, is going to be equal to the sum from n equals 0 to infinity of, I have an extra plus 1 here. I want to try to get these two things, e and 2, to have the same power. So let me take out the e to the 1. So that'll be 3/e to the 1. I'm kind of moving the e to the 1 underneath the 3 since it doesn't have a power. Now it'll leave me with 2/e. Both of those at that point would be to the n because I moved the first power e out. 2 divided by e, that is less than 1. There's my R value. And e is like 2.7 something, so 2 divided by e is less than 1, and therefore this series converges. It's a geometric series that converges. There we go. All right. What about this guy over here? About this guy over here. This is interesting. The only thing that has an n is that -1, so this is really, we want to kind of think about it this way. The sum from 0 to infinity. I can kind of pull out that over 3 and just call it 1/3. And then the thing with my n is -1. So what do we know about that? Well, our r value then at this point is -1, right? And the absolute value of -1 is greater than or equal to 1, therefore the series diverges. Now if I wanted to over here, I could have called all these things absolute values in there. Ultimately that doesn't matter unless we're dealing with a situation where the r value is negative. What's going on over here? Kind of similar, but this time our n power thing is in the denominator. So let's go ahead and maybe call like this, n equals 0 to infinity of, I'm going to pull that -5 out in front, that'd be -5. What will that leave? That'll leave 1/3 to the n. Notice I can pull the n out in front of the 1 also, because 1 to the n doesn't really matter. This n could also be over the 3, it would be the same thing, but now we know that here the r value is 1/3, and that is less than 1, or in other words, the absolute value of 1/3 is less than 1, and therefore the series converges. Alright, I'm going to go ahead and pause the video. I want you to try E and F. Determine the r value for each of those, and determine if the series converges or diverges, please. Alright, I'll walk through it here. Let's see, we want to try to get the same n powers here, so we can use a similar thing to what I did earlier. This would be the sum from n equals 0 to infinity. I can keep that -1, back up for a second. Keep that -1 to the n looks fine, but that 6 to the n minus 1, I'm going to pull out that 6 to the -1 out here. So we have 6 will now be to the n. That way -1 and the 6 have the same power. I did pull out that 6 to the -1 out in front. If you want to do 6 to the -1 in the denominator, you can flip it up and be +6 up top. Regardless, our r value is over here, right? R is -1/6. R is -1/6. The absolute value of that, the absolute value of -1/6 is less than 1, and therefore our series converges. And we can say it converges because it's a geometric series with the r value, absolute value of r less than or equal to 1. Right, what about this guy over here? We got another sort of exponent mismatch. So I can say that this is going to be equal to the sum from 0 to infinity of pi n to the -1. I want to pull out the pi to the -1 out in front. That'll leave me pi to the n over e to the n. So I can say just pi over e to the n. So we go, okay, well, what's happening here? Pi is bigger than e, 3.14, 2.71. So this inside part, we now know that r is pi over e, and that is greater than or equal to 1. Therefore, this geometric series diverges because it's a geometric series with an r value, absolute value of r greater than 1. All right? So there's a quick recap of determining convergence of geometric series, okay? Now, if we want to sum up an infinite geometric series, that we have another formula for, one we should remember, that if it is a convergent series, geometric series, the absolute value of r is less than 1, then a geometric series converges, and its sum will be exactly this: a, that starting value, when n is 0, if it's in this form, over 1 minus r, where a is the first term of the geometric series and r is the common ratio. So if we know the series converges and we can determine the first term and r, we can actually figure out the sum pretty quickly, which is a nice, it's really important fact that we can apply to lots of series to make even more complex things nicer to deal with. Let's do it on sort of a basic level today. Fine. We want to determine if the following geometric series converge or diverge. If the series converges, find the sum. All right, look. So basically we can do what we did last time. We can sort of apply our basic geometric series rules. This thing would be the sum from n equals 0 to infinity of, let's see, the 2 I can kind of pull out in front. That'd be 2 times, that'd be 1 over 4 to the n. So I can do that. What do we know here? This is in our a r to the n term. our first term is our zeroth. In this case, if I plug in n equals 0, gets rid of that. 2 is our first term, so a is 2. So if I plug in 0, you can check over here too. N equals 0, that'd be 2 over 1, so 2 is our first term. And our R value is 1/4. It looks like it converges, right? No major problems there. So we can say that the R equals 1/4, which is less than 1. Therefore, it converges. I'm abbreviating a lot of stuff today, but you would want to write all this stuff out. It converges. Then our sum then is going to be 2 over 1 minus 1/4. And then you could spend the time to clean that up to 8/3 if you wanted to, but I wouldn't. I would just leave it there. Okay. Cool. Let's take a look at the next one here. Looks a little more complicated situation, right? A more complicated situation. We want to try to figure out the first term. We can do that just by plugging in 2. That's fine. We can do that by plugging in 2. But things look a little more complex. Let's do a little work here. This is going to be the sum from n equals 2 to infinity, right? Of, this is looking a little interesting over here, right? Let's, I see there's an e to the minus 4, so let me pull that part out. So that'd be 1 over e to the minus 4. What does that leave? That's a 4 there. Wow, that's a weird looking 4. What does that leave on the inside with all the n stuff? That'd leave pi to the n, right? Pi to the n over, there'd be an e to the 2n on the inside still, right? Interesting. So our series then, n equals 2. This looks, I don't like this, 1 over e to the negative 4, so let me just call it e to the positive 4. I can flip that back into the numerator. Notice I have n's in both the days. Remember, if you have a power to a power, it multiplies in. So this n has multiplied this 2. So if I want to, I can actually say that this is equal to pi over e squared to the n using our properties of exponents, right? Because this n represents pi over e squared times itself. So I just kind of pull it out of the powers of each of those. We can do that. So there we go. There is our series I'm looking at here now. Okay, so what do I do with this? What is our first term then? If I plug in 2, what do I get? I would get e to the 4th times pi squared over e squared squared. So my e to the 4th would cancel out. I'd end up with pi squared, right, as my initial term. If you can't do that all in your head, it's okay. Just like write out the steps. That if n is 2, we get pi squared over e squared squared, so that'd be e to the 4th out in front times pi squared over, if n is 2, e squared squared, e to the 4th, or e to the 4th cancel, we get pi squared. What's our R value? Our R value is pi over e squared. This is less than 1, so it converges. And then I can say my sum is going to be equal to pi over 1 minus pi over e squared. Whatever that's going to come out to be, right? Okay, keep going. This one looks, oh, thank God it let me a little easier. All right, it looks pretty safe that we have, when n is 0, e to the 0 is 1, that those go to 1, so our starting value is 2. Looks like our R value, think about this, is 3 to the n over e to the n, so that's 3 over e to the n. 3 over e, wait a minute, 3 over e, that's going to be greater than 1, so this diverges. Right. What about this guy over here? Interesting. Let's go ahead and let's do a little rearranging of this. I could go ahead and take out, there's a negative 1 in here, so I can say that this is the sum n equals 1. If I take out the negative 1, that'll be e negative 1/2 to the negative 1 times negative half to the n will still be there. So negative half to negative 1 would just flip this, right? So that would really give us that this sum is n equals 1 to infinity of negative half to negative 1 flips. That'd be negative 2, so negative 2e to the negative half to the n. So it looks like when n is our first term here then, when n is 1, I plug in 1. it'd be negative half times negative 2. So it could be positive 1e. So my first term is just e. My r value is negative half. The absolute value of negative half is less than or equal to 1. So it does converge, right? And then we can go ahead and do our sum, which would just be e over 1 minus our r value. So it's minus half, so it'll be plus half. And whatever that sum comes out to be. Another thing you could do if you have this kind of simple situation where you have like n equals 1 to the n minus 1, we could sort of re-index this is what they say. If we subtract 1 here, we could add 1 here and just kind of reset this stuff. That kind of, without much explanation, can get a little confusing. So I like to just do it this way, see what the exponents. All right, what I would like you to do is go ahead and I want to do A for you, then I want you to try part B and see if you can do it too. Consider the geometric series. So we have a geometric series. K is some constant number. We want to find K such that this sum equals 3. Well, if this sum equals 3, it's a geometric series. So if the sum equals 3, we're dealing with our sum formula, which looks like this, right? 1 minus r. We know that the sum is 3. The sum is 3. A. Can we figure out what A is? Well, when n is 0, I plug in 0 there. K over 3 to the 0. That'll be 1. That'll go away. So my starting term is 2. A is 2 over 1 minus r. Well, what do I know r is? R is going to be K over 3, right? K over 3. Weird looking K. Sometimes my computer hangs on with me. Sometimes it doesn't. Okay, so this now has an equation that we can solve for K. Oh, that's kind of nice, right? Let me go ahead. There's like lots of ways that we could approach this and use our algebra to solve it. What I'm going to go ahead and do here then is we could, for example, multiply this denominator to the other side, divide by 3. Let me bring this up here. I can multiply 1 minus K over 3. To the left, I could divide 3 to the other side. Then I could subtract 1 over there, so that can be negative K over 3 equals negative 1/3. I could then multiply negative 1/3 over here to this side. So, multiply by negative 3. That'll cancel out that negative sign and that 3. Multiply negative 3 over here. And we would find K equals 1. But you're like, wait a minute. How do we don't necessarily need to go through all of those steps. If we had a calculator, you're right, and you will have a calculator for the test, so I mean you could have solved this a little more easily. But that would be how you would do it. Go ahead and pause the video and try part B. All right. So we can use a similar process. We know what it sums to. We know it sums to 4/3. Looks like our A value is yet again 2. 1 minus K over 3. The steps are going to pretty much be the same here. We can multiply 1 minus K to the 3 to the left. We could multiply 3/4 to the right, so that'd be 1 minus K over 3. Multiply that whole denominator to the left. Multiply 3/4 over here to the right-hand side. So 3/4 cancels out the 4/3 times that. You have a 6/4. All right. Subtract 1 over there. That'll give us negative K over 3 equals. If I subtract 1 over here, I would get 2/4. So that's half. Multiply negative 3 to both sides. So then K would have to be. Multiply that over there and multiply negative 3. Would be negative 3 halves. Again, if that's going fast, just take your time, go through your paces, solve this equation using your algebra. Okay, there's geometric series. All right, convergence of a p-series. So what's a p-series? A p-series is another one of our important series. A p-series is defined here as sum from 1 to infinity of 1 over n to the p. So 1 over 1 to the p, 1 over 2 to the p, 1 over 3 to the p, and so on and so forth. And if p is greater than 1, this p series will diverge. If p, though, is between 0 and 1, if p is between 0 and 1, including 1, it diverges. P has to be positive. If it was negative, it would flip it up to the numerator, and then it would automatically diverge or whatever. So if you want to, we could probably extend this to say, if p is less than or equal to 1, then it just diverges. All right. A special p series, that's a harmonic series, a situation where p is 1, so n equals 1 to infinity of 1 over n, is our harmonic series. And our harmonic series is that one sort of right on the boundary of this when p equals 1, and it diverges. So let's determine if the following series down here converge or diverge, and identify any values for p if we have p values we need to solve for. I don't think I gave us any of those practice ones right now. All right, so what is this? We want to get into the form 1 over n to the p. So this would be the series summed n equals 1 to infinity of 1 over n to the cube root of n would be 1/3. So let's see. Oh, wait a minute. We can tell this right away. It's pretty quick. We can see that this is a p series where our p value equals 1/3. And we could say, okay, 1/3 is less than or equal to 1. So our p series diverges. Okay. What do we got with this guy? This one's interesting. We have a -2 in front. This is just some common factor. It's going to be present in every single term. So in series, it is kosher to be able to just sort of factor that out of the series, because it's just going to be in every term. So we just multiply the whole series by it, just like we can do that with derivatives and integrals. And that will leave us with 1 over n cubed. So what is 1 over n cubed? Oh wait, that's a p series, so the p equals 3. P equals 3, right? If p equals 3, and therefore this series converges, I'm going to write everything out. It converges because it's a p series with p equals 3, or p is greater than 1, I'm sorry. All right, we got some things over here. We got n's. Both of these can be represented with power, so it looks like this is something we're going to have to use exponential rules for. That's n to the -2 times n to the positive half. So if I use those, my exponential rules, this will be n to the negative half, right, is what I would get when I combine those. N to the negative half would be what I would get when I combine. Oh, I made a weird mistake. It's not n to the negative half, because I wrote a number down wrong. That should be -2. So adding these together, -2 plus half, if we're same base, we can add the exponents. That'll be -3/2 left. If you have trouble with the fractions, write it out. -2 is -4/2 plus 1/2 gives us -3/2. What does that mean? This is a series then that looks like this. 1 to infinity of 1 over, let's see, into the -3/2, that's 1 over into the +3/2, right? So this is a p series where p is 3/2. Then we can say it converges because, we're not going to write everything out, it converges because p is greater than 3, or sorry, p is greater than 1. Converges because it's a p series with p is greater than 1. All right, so that's what we need to be on the lookout for convergent p series, okay? And as was kind of teased up here, though it didn't give any problems, sometimes we can even solve for what that value needs to be to make it converge. If we know that, right, we know that the p needs to be greater than 1 for it to converge. Let's talk about the alternating series test. We'll actually kind of slam these two things together. So the alternating series test says, let a sub n, so whatever sort of the main part of the series terms is, be greater than 0. If it's greater than 0, we don't have to worry about negative signs there. The alternating series, so as long as these series are alternating, and they need to actually be alternating, which sometimes you need to check. If the series is actually alternating, positive, negative, positive, negative, positive, negative, or negative, positive, negative, positive, negative, positive, either one. If the series is actually alternating, then the alternating series will converge if the following conditions are met. If the limit as it approaches infinity of this inside term is 0, and a sub n plus 1 is less than or equal to a sub n for all n is greater than big N, where n is some integer. So what does this mean? This means that eventually, so if a sub n plus 1 is greater than a sub n, that means that the a sub n part here needs to end up decreasing. All right? So alternating series test is actually kind of nice because we have, if you think about that very first day, it's not technically on the AP exam, but I want to bring it up here, that we do have the nth term test for divergence. The nth term test for divergence says a series will diverge. A series will diverge if the limit as n approaches infinity of the individual terms does not equal 0. That's what the nth term test for divergence said, that if you actually just take the limit of the individual terms inside of the series, then if the limit does not come out to be 0, then the series just diverges. But it doesn't tell us what happens if the limit is 0. What's nice is the alternating series test does include that if the limit comes out to be 0, then actually we can tell that the series diverges. If it's an alternating series, the limit goes to 0, and the terms are decreasing eventually. So this is a situation where on the test you actually do need to show that certain conditions are met, okay? So when we're doing this, we do need to actually show these things are actually true. So let me go and do like an example here to kind of help you out, okay? Let's determine the convergence or divergence of this specific series, okay? So question we have to answer first is this series alternating? Let's see, it has a -1, and then square root of n plus 1, as n goes from 0 to infinity, that will always be positive. So we can say, if it helps us out, it's nice to kind of define stuff. We can say a sub n is 1 over square root of n. Basically, we ignore the alternating part of this. And a sub n is greater than 0. Great. So we've now established that this thing is actually alternating because the negative part will flip every time the power goes up by 1. But the other stuff, the a sub n stuff, will always be greater than 0. So this is going to be an alternating series. Then we need to check that the limit of this stuff, the a sub n stuff, goes to 0. So I check the limit as n approaches infinity of 1 over square root of n plus 1. I say, well, what's going to happen with that? As n goes to infinity, the denominator grows. So 1 divided by a big number means that a sub n will go to 0. Great. So as I'm going down the checklist, I've established that my a sub n's are greater than 0 after I kind of ignored the -1 part. They always will be greater than 0. I've also established that the limit of as n goes to infinity of a sub n is 0. I now need to establish that my terms are going to get smaller. This is where we have to actually do a little bit of work, right? So I can say that I need to compare a sub n plus 1, which if I take my a sub n, and instead of a sub n, call n plus 1, that'd be 1 over square root of n plus 1 plus 1, so that'd be 1 over the square root of n plus 2. Basically, I'm just adding 1 to my term there. And then I know what a sub n is. Let me compare them instead. So 1 over square root of n plus 2. 1 over square root of n plus 1. I need to ask myself, is my a sub n plus 1 going to be less than or equal to a sub n? And in this case, right, is it less than or equal to? In this case, it will be, right? Because if I'm adding something to the denominator here, this denominator is going to be bigger than this denominator. 1 over a bigger number will make this thing smaller. So I can say that is true because the denominator, it's kind of good to overkill the denominator, gets larger, we could say gets larger as n grows. All right. So then we've established that this is true. All three things have been met. And so we can say that, I'm not going to copy the whole thing down. You should, the sum from 0 to infinity of that stuff, and you would copy that over there, converges by the alternating series test. And then you would write out alternating series test. Right, but you have to show this positive thing, the limit of a sub n goes to 0, and that eventually you get to the point where your a sub n plus 1 is big or is less than or equal to your a sub n. Okay? Let me give you another slightly more complex example here. Okay. In this example, let's see what we got. Looks like it could be an alternating series, right? So let me define my a sub n. My a sub n then would be 1 over n squared minus 6n plus 10. So I go, okay, is this part of this thing going to be positive, right? Is this thing going to be positive? For n is 1 to infinity, right? N is 1 to infinity. So if we want to, we could see if, for example, is it possible to like factor this or figure out if this thing is going to be greater than 0. If we want to, this might be a good place to like pull up, for example, if I could here, a graph to kind of visualize this stuff. Our terms that we're looking at, if I turn this into a function, it'd be 1 over x squared, right, minus 6x plus 10. And so I go, hey, what's going to happen to my denominator? It actually doesn't factor because the x values for all x values is actually going to stay positive. We can see from this curve here. You can also just run a few tests. Just plug some n values in here. No matter what n value you choose, 1 over n squared, whatever, will be positive. So we can go ahead and just state then that this function here, or the a sub n terms are greater than 0. Now you don't necessarily need to work for, you just got to check it yourself and state it. We can check the limit, so the limit as n goes to infinity of 1 over n squared minus 6n plus 10. It got really weird looking. Plus 10. You'll hear me say that a lot. Well, n goes to infinity, so the denominator grows. This does go to 0. So we've checked positive. The limit as n goes to infinity goes to 0. Now we gotta get to the hard part. Here's what's difficult. It's hard to tell. It's hard to tell, right, what's going to happen here when n is greater than 1. Okay. So one tool that we can use if we want to is we would like to know, if possible, we would like to know whether or not this denominator is like getting bigger or getting smaller. So actually a derivative is kind of nice. Let me take the derivative of the denominator. If I take the derivative of the denominator, what do I get? The derivative of the denominator will be 2n minus 6, right? So you go, well, what does that tell us? What does that tell us? Well, think about it. It has a 0 at 3. So when n is greater than 3, when n is 4, 5, 6, 7, 8, 9, 10, those kind of things, right? Then our derivative is positive. If the derivative is positive, that means the denominator will be increasing. Right? So the denominator does increase. Denominator increases when n is greater than 3. So the fraction gets smaller. Sorry, if the denominator is increasing, the fraction is getting smaller. Right? If the denominator is increasing, and we show that using the derivative. When n is greater than 3, the derivative is positive, so the denominator is increasing when n is greater than 3. So the fraction is getting smaller. What does that mean for us? It means that a sub n plus 1, as n gets bigger, eventually that is going to be less than or equal to a sub n, because the fraction will eventually get smaller. Okay? If you want to, it's a little time consuming, but you could plug in like a sub 1, 2, 3, 4, 5, 6 and prove to yourself that this will eventually start decreasing. But a derivative can help speed that process up. So we've now proved everything. So that is going to be true when n is greater than 3. So it eventually decreases, which is all we want to show. And then you can say, therefore, my series n equals 1 to infinity of whatever, and you copy that down there, converges by the alternating series test. Right, there's that. Well, what I'd like you to do now is go ahead and show that this series converges. Pause the video and practice that. All right, so it looks like our a sub n in this case is going to be 1 over 2n factorial, and that is always positive, right? So that's good. We need to show that the limit as n approaches infinity of 1 over 2n factorial goes to 0. Well, think about it. As n gets bigger and bigger and bigger, 1 over 2n factorial, that's going to be huge, is going to go to 0. Great. Now we got to prove then that a sub n plus 1 eventually is less than or equal to a sub n. We can do a quick little check. Maybe this isn't really a thing we can take a derivative of. So we could do a direct. Let's plug in n plus 1 for n. So that'd be 2n plus 1 factorial. So this is, I'm finding a sub n plus 1. What I'm doing here. What does this neaten up to? That gets to be a little weird looking, but it'd be 1 over, think about it, 2n plus 2 factorial. Okay, so 2n plus 2 factorial. If I compare that to 1 over 2n factorial, the denominator here is bigger, right? 2n plus 2 versus 2n. So I could say here then 1 over 2n plus 2 factorial is less than or equal to 1 over 2n factorial. Therefore, a sub n plus 1 is less than or equal to a sub n. And then I can say that my series converges by the alternating series test. Plug that thing in there, plug this down in here, converges by the alternating series test. And you would write out alternating series test. All right. Again, you need to show these things, right? We've seen on some of our FRQs you have to show your conditions. Okay. So I want to wrap up with a quick sort of combination of these two things. Now, absolute and conditional convergence is not on the test this year, but it can be a convenient tool. So it is one maybe to have in the back of your mind, okay? Just because something's not required on the test doesn't mean you can't use it if you feel like it's necessary. I would point out that like a few years ago I had a kid in calculus taking his ACT, couldn't remember how to find the vertex of a parabola, and so used calculus to do it. The ACT does not require that you know calculus, but it was a tool he could use to quickly find a vertex of a parabola. So, definition of absolute or conditional convergence. We'll dig into this more after the AP exam, but we say that a function or a series is absolutely convergent if the series of its absolute value converges. We consider absolute convergence like a stronger version of convergence. Basically, we're determining whether or not a series would kind of converge on its own without any alternating things. We say it is conditionally convergent if the series by itself converges, but the absolute value of it does not. The absolute value of the terms does not. Okay. Quick examples here to test absolute convergence. Okay. Some quick examples. Where's my notes? Okay. So, I guess I should say the good thing is that if you can prove that something is absolutely convergent, it means that it is convergent. We're kind of done there. It's kind of like all squares are rectangles, but not all rectangles are squares. The series, if something's absolutely convergent, it is convergent. But just because something is convergent doesn't mean it's absolutely convergent. Okay, let's take a look at this one. Let's check its absolute convergence. So I'm going to say that the series 1 to n, I'm going to take the absolute value of the inside. The nice thing about absolute convergence is it does make dealing with some of these series a little easier because we can kind of get rid of all those negative sign things we've just been dealing with our alternating series. Well, wait a minute. Oh, that's easy if we take the absolute value. That's going to be equal to n equals 1 to infinity, right, of the absolute value would kill the negative part here. N to the 3/2, if n is 1 to infinity, will always be positive, so I can kind of just actually lose my absolute value signs after I get rid of my negative component of this. All I'm left with is this, and that's really easy, right? This is a p-series with p is greater than 1. So, this I should say converges. It is a p-series with p is greater than 1. So what did I just prove? I just proved that my series, and I would copy that stuff in there. You can do that. My series, don't write squiggles, please. Actually copy that down. Converges absolutely, or is absolutely convergent. Again, to recap, why? Because I was given a series. I took the absolute value of the terms. I got another series. I found that that series was convergent. This one happened to be a p-series with p is greater than 1. Therefore, my original series is absolutely convergent, or converges absolutely. Right? Okay. So, let me take a look at this one here, right? Interesting. Let me take the absolute value, and I can check absolute convergence. If I do that, n equals 1 to infinity, take the absolute value of that, negative 1 to the n over 8. That'll give me a series that looks a little goofy, just 1/8. So think about it, if I'm adding 1/8 plus 1/8 plus 1/8 plus 1/8 plus 1/8 plus 1/8 on and on to infinity, then this has to diverge. It's not going to get a finite thing. We could also use the nth term test if you want to. You can say the limit as n goes to infinity of 1/8. Well, what happens is n goes to infinity 1/8. There is no n, so this just stays at 1/8, and 1/8 is not 0. Remember, the nth term test says take the limit as n goes to infinity, the inside part. If it's not 0, then the thing diverges. Okay. So I just found out that the absolute value thing diverges. It's not absolutely divergent. Right? It's not absolutely convergent. It's not absolutely convergent. It may be conditionally though. So let me go ahead and just check. Now I actually have to check the whole series. So I would say n equals 1 to infinity, negative 1 to the n over 8. It kind of actually looks like a geometric series. So let me rewrite it in geometric series form and figure out if it's going to converge non-absolutely, or conditionally we say. So I'm going to take out the over 8. That'll be 1/8. I have negative 1 to the n. Okay. We have a starting value of 1/8. Our r value is negative 1. So what do I know here? That this thing here, if it was a geometric series, is a geometric series with an r value, an absolute value of r value. Absolute value of r value that is greater than or equal to 1, because my r value here is negative 1. And therefore, my actual series, and you would copy to there, is divergent. So I tried absolute convergence first. It failed. Then I had to check the actual series here to kind of figure out what's going on. And it turns out that series, right, the geometric series test would show that it diverges also. Everything, it just diverges. Divergent series. Okay. What about this guy over here? Okay. I could check a few things. What do we got? We could take the absolute value. Sorry, to kind of wrap my mind around things first. So I take the absolute value of it. At the same time, are you cool if I just don't write the whole absolute value step? I'll take the absolute value of the inside, and I would get 1 over square root of n. You know what? That's bad math. I'll do the absolute value. Come on, Mark. Stop writing squiggles and skip the steps. All right, there we go. This is going to be equal to the series equals 1 to infinity of 1 over square root of n. But square root of n is n to the half power. So what does that mean? What does that mean for us? This looks like a p series, right? It's a p series. A p series with p is less than 1, right? So I can say this is a p series with p is less than 1. P is less than or equal to 1, I should say, for p series. Therefore, it diverges. So we just found out that my series is not absolutely convergent because this absolute series diverged. Okay, so it's not absolutely convergent. Let's check just kind of the natural series here without the absolute values. So now I come down here and I check. It equals 1 to infinity of negative 1 to the n over square root of n. Looks like I could use the alternating series test. Alternating series test, a sub n would be 1 over square root of n, and that would always be greater than 0, so that part is good. The limit as n approaches infinity of 1 over square root of n. As n grows, that will go to 0, so that's good. So far, the alternating series test is saying that this series does converge, but we just proved it won't converge absolutely. So what do we do here? We now got to check whether or not 1 over square root of n plus 1, remember a sub n plus 1, whether or not that is less than or equal to 1 over square root of n. And it will be, because denominator of 1 over square root of n plus 1 is greater, is larger. So we can say a sub n plus 1 is less than or equal to a sub n. Check. Alright, so we just proved that our series, the actual original series, equals 1 to infinity of negative 1 to the n over square root of n converges conditionally. Converges conditionally, or is conditionally convergent. We know that because when we checked absolute convergence, it turned out it was a p series that diverged, but the actual base series by the alternating series test, we could set that down here, by the alternating series test, our series is conditionally convergent because the natural series converged, but the absolute series did not. All right, I'm going to go ahead, pause the video, and try this last one. All right. Looks a little more complicated. We can start off with the absolute stuff. N equals 1 to infinity of, I take the absolute value of everything, negative 1 to the n minus 1, 8th root of n over 2n would give me the series n equals 1 to infinity of it. I would lose the negative 1 part of this. I would have n to the 1/8 power, right, over 2n. Right. Over 2n. This 2 I actually don't need to worry about. It's like having a half in front of this. So if I want to, I could actually just go ahead and like pull that out in front, so I don't have to worry my mind about that stuff. So what does that simplify to? This would simplify to 1/2 the series from n equals 1 to infinity of, see, I'm going to bring that to the denominator, right? If I want to combine these, I can think about, n to the 1/8 power. This is n to the 1 power, so the denominator, so I can subtract 1/8 minus 1 will give me n to the negative 7/8, into negative 7/8, or 1 over n to the 7/8. That got real crazy. 1 over n to the 7/8. Bring that to the denominator, and I'm going to subtract it. So there we go. What does this mean? So absolute convergence wise, here's the problem, right? This is a p series with p is less than or equal to 1, therefore diverges. And we could say, kind of think in our mind, our series is not absolutely convergent then, but it could be conditionally. So let me check sort of the natural version of the series. We go through all the same processes we did over here. I'll run through those real quick. The a sub n, if you kind of take out the negative sign, our a sub n is 8th root of n over 2n. We can even factor out that 2 like we did over here and just say 8th root of n over n. So our a sub n is 1 over n to the 7/8, which is greater than 0. So that's fine. We can check that limit. The limit as n approaches infinity of 1 over n to the 7/8 does go to 0 as n gets bigger, and then we would have to check whether or not the series ends up getting smaller, and I'm not going to write everything out here, but 1 over n plus 1 to the 7/8 is going to be less than or equal to 1 over n to the 7/8. Why? Because the denominator here is bigger than the denominator over here. So therefore, n plus 1 is less than, sorry, a sub n plus 1 is less than a sub n. And therefore, our series is here, the series I started with, is conditionally divergent. Sorry, conditionally convergent. Oh my gosh. It was not absolutely convergent, but by the alternating series test, it passed all the alternating series test things. Then our original series here is conditionally convergent. Not absolutely convergent because the absolute value stuff diverged because it was a p series, but the base series was divergent, or sort of was convergent, so it is conditionally convergent. All right. Cool. That lays the groundwork for a lot of our series work. For homework, got some practice, 3 pages. These aren't real FRQs. They're actually just practice, so I want you to work through the 3 pages. Answers and help will be online. Just correct yourself and send me the corrections in a different color, please. All right. Talk to you all later. Bye.